All right, good afternoon. Thanks for joining us. We'll go ahead and get started here. I hope you can hear me okay. I'm on a little bit different setup than normal. So as we go through today, if you have any questions, feel free to ask them using the question and answer interface in Zoom. That is what I can see as we go through. If you send something in via chat, I have to stop and move stuff around to be able to see it. So if at all possible, send it in using the question and answer interface. So today's webinar is our Wi-Fi 101 webinar. I've been working here at Zyxel since 2003. Most of that time has been with Wi-Fi products in one form or another, and it's still something that I do not consider myself an expert in. You know, it's one of those challenges when you're dealing with something that you can't see it, you can't feel it, but it is interacting with all sorts of stuff in the environment around you. And you can really run into situations where, you know, it seems like it should work, but it doesn't. So today's webinar is sort of going through the background, how we came to be where we are today, and covering, you know, some of the background and some of the core mechanics of how Wi-Fi operates, how it works. Just to give you a little bit extra knowledge and maybe help you when it comes to, you know, designing networks or troubleshooting networks that are having issues. So for those of you that are new, I want to do just a brief one-slide quick summary on who Zyxel is. So we've been making computer networking products since 1989. That is our core business, and we've been at it for a real long time. We had wireless Wi-Fi products back in the days of 802.11 before they added the A and B signatures or extensions onto them. So we've been at this for a long time, both Wi-Fi, modems, firewalls, switches, you name it. We've got over 100 million devices that we've deployed out in the field. We serve 150 different global markets. The U.S. and North American office is located in Anaheim, California. So that's where our sales team is, that's where our warehouse is, and that's where our tech support is. So we don't outsource our tech support. When you call in, you are getting somebody here at our Anaheim office who's a Zyxel employee. Or if you're calling in the morning, early morning West Coast time, you may be transferred over to our German office and their tech support team. So now we'll go ahead and get started on the webinar. So the first thing to talk about is some of the players in the space. You will see these names being thrown around a lot when talking about different issues with Wi-Fi. So there's the IEEE. They're the industry group that gets together and puts together the official standard. So when you see something with Wi-Fi and you see 802.11, A, B, AC, whatever, that is referring to the IEEE spec that defines how the product is supposed to work. And of course, if you look at the data sheet or have been around networking for a while, you'll see various other 802 standards being used on switches and things like that. So they're the guys who do it, and they're the first step when it comes to creating a new standard. So when we go from AC to AX, they're the guys who created that. On top of that is the Wi-Fi Alliance. So the Wi-Fi Alliance came about because even though we've got these good IEEE specs, you know, there's always room for interpretation on certain things. You know, no matter how hard you try, you know, the English language isn't necessarily absolute. So what happened is especially in the early days of products, is there was a lot of compatibility issues. You know, you would have an 802.11b access point, but for some reason it wouldn't work with one of your 802.11b client adapters. So one of the main things the Wi-Fi Alliance did is they came together and they provided testing and certification of products, primarily aimed at interoperability. They're also a marketing organization. So they're the ones who have created the Wi-Fi logo. They're the ones, so if you're buying products, especially consumer products, you'll often see this Wi-Fi logo that's down there on the bottom of the slide. They're the ones who come up with that. They're the ones who do the testing and enforce that. You can always go to their website and they've got a list of all the certified products. Having said that, they are primarily aimed at the consumer space. You will not find a lot of business class product that bothers to pay the extra fees to get Wi-Fi certified, especially these days where product compatibility is pretty much hashed out without needing the testing. The Wi-Fi Alliance is also the one that decided to rebrand 802.11, ABG, et cetera, into Wi-Fi 1, 2, 3, 4, 5, and 6. So, the new 802.11 AX IEEE standard is now known as Wi-Fi 6. The old 11 AC standard is now known as Wi-Fi 5, et cetera, going backwards. And then last but not least is the FCC. So the FCC is basically who gets to set the rules for using wireless airwaves. So they tell you basically what frequencies we can use. They tell us power output rules. They tell us band edge behavior, etc. So every product that is sold in America has to be in compliance with FCC regulations. Now the FCC, they set these rules, but they don't actually do much or if any enforcement of product being deployed. Basically, for any product that's going to be launched here in North America, the manufacturer pays to get the product tested and verifying that it meets the requirements and submits the paperwork to the FCC to allow the product to be imported. But they don't normally do any sort of checks or things like that afterwards, and that has caused problems in the past. A number of years ago, I believe it was Netgear sued ASUS because the ASUS products that were actually being imported didn't comply with FCC requirements, so it required Netgear to sue to force them to actually comply with the rules. So going on there, Wi-Fi works using radio waves, right? It's basically the same thing that powers an over-the-air television station, powers a radio, AM, FM, your walkie-talkies, etc. What's different is just the frequencies being used. So the FCC has come along and chopped up the available spectrum into different chunks. And for the most part, if you are going to broadcast radio waves, you have to have a license. But what they've done is they have opened up chunks of the spectrum that basically anybody can use. So you've got the 900 megahertz frequency range, 2.4, 5 gigahertz, and I probably should add it to the slide. They've recently opened up a chunk of the 6 gigahertz spectrum for unlicensed usage. So that's what any sort of consumer or most of your business class products are going to do. They're going to operate in one of these three spectrums. So it's not just Wi-Fi, it's your Bluetooth devices, it's walkie-talkies, it's cordless phones, it's all sorts of other stuff that is using wireless of one form or another. They'll be using one of these three chunks of spectrum. So one thing to keep in mind when you're looking at this is as frequency goes up, it's easier to cram more data onto it using the same amount of bandwidth, but the range goes down. So going back to these three chunks of spectrum, these have been used in the past for cordless phones. And if you're old as dirt like me, you will remember the days of 900 megahertz cordless phones. They were fantastic as far as range goes. I remember being able to walk down the street to a friend's house nearby and still being able to maintain a phone conversation. The problems you ran into it were the sound quality wasn't that good. Oops, and thank you, Stuart. I see your comment there that I have got a typo, which I do. I will try to remember to fix that next time. Thank you for bringing that up. Anyway, back to my story. Sound quality wasn't good, but it also had a lot of problems in like apartments and condos where you had a lot of users in the same area. There just wasn't a lot of a non-overlapping bandwidth to use, and you would run into situations where you'd be talking to somebody and then you would hear somebody else's conversation who was also trying to use that same frequency. So there was a move in the late, I want to say it was the late 80s, to 2.4 gigahertz cordless phones. It opened up a much larger chunk of spectrum because you could cram more data on there. You were able to get higher sound quality. There was also some other technology increases like going from analog to digital at some point along those lines. But it also allowed you to fit more phones in an area before there was interference issues. But you couldn't go as far. And then after that was the 5 gigahertz cordless phones. Again, much better sound quality than the 2.4. Less interference issues, but the range was a lot less. So you went from the days of 900 where you could walk, depending on the environment, outside your house and down the road a little bit, to 5 gigahertz, where if you've got a larger McMansion home, you may not get full quality coverage throughout your entire house from a single base station. And it's the same thing here with Wi-Fi. So, in general, power is being measured as dBm. You will see it measured primarily as EIRP, which will tell you the frequency being radiated out from your antennas on a device. Most data sheets these days will list power as dBm coming out of the chip, and then they will list the antenna gain separately as dBi, and you can add those together. One thing that happens is you will notice if you're looking primarily at consumer-grade equipment is they tend to market their products in milliwatts instead of dBm, where most business-class products will list power as dBm. So why is that? It's primarily a marketing gimmick. So with every 3 dB gain of power, you're essentially doubling the milliwatt rating. And so it looks a lot better to say, you know, we have a 200-watt device, our competitors are 100 watts, versus saying we have 23 dB of power, our competitors are 20, right? 200 versus 100 looks much more impressive than 23 versus 20. So that's a big part of it right there. Because of the way Wi-Fi signal degrades, when you double the power, you do not get anywhere close to doubling the range. And we'll talk a little bit more about that on an upcoming slide. The other reason business class products tend to use dBm is because oftentimes those products allow you to replace the antennas, or you're more likely to use that type of product for your own custom, you know, outdoor point-to-point link or something. And you can easily add the dBm coming out of the chip to the antenna to get an estimate of your EIRP. Although ideally you'd also want to take into account, you know, wire loss and connector loss and things like that. And those of you that are doing a lot of outdoor work, particularly point-to-point work, do take all of that into account when trying to calculate how far of distance you can get, what your link budget is. So something that tends to get overlooked a lot, and is probably actually, though, the single most important factor when it comes to Wi-Fi performance, is the signal-to-noise ratio. And that's simply measuring the signal, the thing you want to hear, versus other RF sources operating on the same or neighboring frequencies. So it's similar, think of this to just having a conversation with somebody. If you and your friends sit down at an empty bar and talk to each other, you can talk at normal voice volume levels and hear each other just fine. But as the night goes on and more people come into that bar, you start getting a lot of noise from the other people talking, other people dancing, maybe the music comes on. That is all what would be considered noise. So now you cannot hear each other as well, and conversation becomes more difficult. So you've got to start shouting or speaking louder to be able to hear yourselves over the noise. So that's your signal-to-noise ratio. Another term here you will see often used is attenuation. It's basically saying how much the signal is degrading as it travels through a distance. So as signals travel through air, they degrade, and depending on the medium, they'll degrade more or less. So if it tends to be, you're in a humid place, humidity will absorb more of the RF signal, so your attenuation will be higher. You know, building materials like walls and things like that, those also will provide different levels of attenuation. So if you're wanting to calculate just how far that Wi-Fi signal is going to go, here is the formula right here. Basically, you're taking, you know, distance plus frequency, and it'll give you your path loss, how much the signal is going to degrade over that area. So you can plug all those in and try to figure out how far that Wi-Fi signal is going to go. And this is, you know, one of the reasons why, you know, I tend to hate the question, well, how far can I go? You know, how far can I get a signal from your access points? And there's just so many variables that go into it, right? It's really hard to say with any sort of certainty. A simple 200-watt access point is theoretically capable of sending a usable signal over a mile. When there's no RF noise, when you've got it high enough up that there's no obstructions, you've got clean RF line of sight, it is totally theoretically possible. So, you know, obviously nobody is getting a 1 mile range connection on a typical, you know, 200 watt access point. So that's why we don't like it, because, you know, there's things that are going to affect it. Like I was talking about before, humidity can affect it, the weather can affect it, and obviously the RF environment itself. Where are there other sources of RF interference? What sort of materials is the signal going through? Is it passing through walls? Is it passing through people? Is it passing through the office copier before it gets to where it needs to go? And then leading into that, the other problem you run into is that Wi-Fi is two-way communication. Again, just like that conversation in the bar. If you and your friends are talking to each other and you're both speaking at the same loudness, you know, you can hear each other just fine. But if one of you has COVID and you're having a sore throat and you can barely talk, you've almost got laryngitis, right? Your range goes through. You have to get closer together to be able to have that communication, because both sides need to be able to hear each other. And there is a huge mismatch in power output between your access point or router and your mobile phone, your Amazon Fire tablet, etc. So, and I use milliwatts here just to play up the difference here, but you're talking the difference between, you know, a 500 milliwatt or a 1 watt access point and your typical mobile device that's going to peak at about 25 milliwatts of power. So there's a huge disparity here as far as how far that signal can go. So that's something else you really need to keep in mind. One problem we've run into with hotel deployments with some of our VARs has been they will go out and do a proper site survey, but they will be doing it with a laptop that's reasonably powerful. So they'll go in and they'll spec it out and they'll say, great, this access point can cover 6 rooms. No problem, good connection, everything's great. And then when guests start coming in, the hotel starts getting complaints. Why? Because the guests are using, you know, cheap Fire tablets, Walmart tablets, they're using a $99 phone, maybe they're even using an iPhone. The iPhone doesn't have much output power because they're trying to maximize battery life. So what happens is those devices aren't able to get their signal back to that access point where the laptop they were using for their site planning had no problem doing it. So that's always something you've got to keep in mind, is that mismatch. Now, you don't generally want to turn the power down on your access point because most traffic these days is downstream, right? You're downloading your emails. You are essentially downloading when you stream a song or a video or something like that. So by having the higher output power on your access point, it improves your signal to noise ratio. So you want to keep it high as possible, although it does cause other issues with co-channel interference with neighboring access points, and we'll talk about that a little later. Another thing that happens with this scenario here is why you get complaints where you're on your phone or whatever it happens to be, and you've got 3 bars, which seems like a reasonably strong Wi-Fi connection, yet your internet isn't working or it's ridiculously slow. And the reason for that is because your mobile device is showing you the signal strength that it's hearing from the access point. You don't know how good your signal is at getting back to the access point. And again, because of the mismatch in power here, you run into these situations where your phone thinks it's got a good quality connection, but the access point isn't capable of hearing the signal very well coming from your mobile device, which is why you run into those issues. It's also why a lot of mobile devices fail to properly roam between access points. So if you're coming into an office where there's multiple APs, it'll connect to the first AP, and as you move around, it remains stuck to that first AP because it doesn't know any better, because it can still see a reasonably strong signal to that AP, so it thinks there's no reason for it to try to find another access point with a stronger signal to connect to. So that's why oftentimes, in the interface when you're setting up your networks, you want to set a threshold for receive strength here at the access point level, so the access point automatically kicks the client device off when its signal gets too low here at the AP, which in most cases will force the mobile device to rescan and connect to hopefully a nearby AP with better signal strength. So Wi-Fi is invisible and it interacts quite a bit with the environment, which is why it's important here to sort of talk about some of the RF behavior. So radio waves behave very similar to waves in water. So as an analogy, when thinking about Wi-Fi, it helps to sort of picture, converting that Wi-Fi situation into more of like a pond type situation. So your transmitter here that's generating your waves would be something like a rock. So if you throw a rock into that pond, it will generate waves which radiate out, just like RF radio waves do from a Wi-Fi device. Obviously, Wi-Fi is more of a 3D environment versus waves, which are a 2D environment, but it kind of works here for trying to visualize what's going on. So as those waves radiate out, they interact with the environment. So they will hit things and bounce off of them and send new, less powerful waves out in a different direction than the initial connection. They have the ability to hit surfaces and sort of scatter, going off in multiple directions. They have the ability, when they hit a solid object, to actually wrap around it. And that's something you may have seen in, again, with water waves, where they hit like a pillar on a dock. The waves have the ability to sort of wrap around it. And RF waves do the same thing. But unlike water waves, RF waves can also penetrate through many different types of solid structures, just degrading in signal strength as they do so. Another thing I want to talk about here is pre-Wi-Fi 6. This is how Wi-Fi devices determined whose turn it was to broadcast. So with Wi-Fi, or any sort of really radio communications, only one device can transmit at a time. When you have two or more devices transmitting using the same frequencies, you get interference. If you've ever used, walkie-talkies as a kid, the cheap analog ones, you've probably run into that, where if you've got more than two of them at least, where two of you try to talk at the same time, and you just get horrible feedback and garbage noise coming through to that third walkie-talkie that's trying to hear what's being said. So very similar to what happens with Wi-Fi. So the way we determine with Wi-Fi if you can transmit anything is basically what they call sensing the medium. So basically your Wi-Fi device listens to see, is anybody else broadcasting? If nobody else is transmitting, you go ahead and transmit your data. If somebody else is transmitting, the Wi-Fi protocol then uses a random number generator to determine how long to wait. It'll pause and not transmit anything. It'll wait that amount of time, and then it repeats the process of listening to see if something's there. In the early days of 1999, when the first 802.11 specs came out, this was good enough. You weren't streaming video, you weren't streaming music, you weren't making phone calls over your Wi-Fi. You were slowly transmitting files from one device to another. But as usage has changed, and now you're streaming, so we're trying to get a constant connection. As you add more and more devices into this RF environment, this starts to break down. Oops, okay, so I'll save it on this slide for a second. So this starts to break down, and you start running into situations where two devices will decide they want to transmit. They will both listen at the same time, not see anyone else transmitting, and both will decide to transmit at the same time, which then causes a collision and basically those packets to be dropped and you have to start all over again. And also just in general, this is not the most effective medium if something is being broadcast to determine how long you should wait, right? Using a random number generator to determine how long to wait before trying to transmit again isn't necessarily all that efficient. So you end up with dead air time where nobody's transmitting just because no one is determined to check yet. They're all waiting for their next, turn to decide to check if they can transmit or not. There's another issue that's related to this, which is what we call the hidden node problem. And this is an ancient slide, but it illustrates well what we're talking about. So here's our access point, and it's got this big round coverage area where anybody in this area can easily hear the access point and send data back to the access point. What you've run into here is a situation where you've got two different users connected to this same access point. Both want to send data. And while both of these devices are within range of the access point, they are not within range of each other. So what happens is this device listens, or this device starts transmitting, and this device listens. It cannot hear that this access point or this device is transmitting, so it thinks that the RF is free. So it will also start transmitting, and then you get this conflict where packets start getting dropped because the access point isn't able to hear either of them now because it just turns into sort of a RF garbage. So this is another very big problem, especially again in networks where you've got lots of users on there, especially lower powered users where their signal isn't going too far. So the next little thing I want to talk about here is data rate versus throughput. There are many different definitions of what these terms might mean, but what I'm talking about here is just in general is how people in the real world tend to use these terms. So generally you will see products being marketed as having a data rate. It may also be called a physical rate or a link rate. And on some computer stuff, you may call it throughput, but it's basically a measurement of the total data being sent between the access point and the client device. What you will see people normally do, though, is they'll talk about throughput, and they'll use something like Ookla, which used to be speedtest.net, or they'll use some other speed test program to perform a throughput test. So this throughput test isn't measuring the total amount of data being sent between the access point and the client device. It is measuring the amount of data that's being sent from a program on the PC through that wireless connection and then out to another server. And these two numbers can be significantly different when it comes to Wi-Fi. Now, if you're doing this and testing a Ethernet Cat6 connection, the differences between the data rate and the throughput are very minimal. But when it comes to Wi-Fi, they can be as much as 60%. So why is that? And that's just because in order to make Wi-Fi work in this RF environment where there may be all sorts of other RF devices operating, whether they be other access points nearby, whether they be video game controllers, whether they be smart home devices, whatever it happens to be, they're all using this unlicensed spectrum. So you've got to put in a lot of protocol overhead that goes into it, that is additional data that is sent between the client device and the access point to make Wi-Fi work. And it is a huge amount of overhead overall. And you will see similar behavior in like power line products, which run into the same issue. So what you'll see if you go to Amazon reviews is, you'll see a product being advertised as let's keep it simple, an N300 device, 300 megabits per second wireless. And you will see lots of negative reviews of people saying, hey, I did a speed test with Ookla, and I only got 140 megabits per second. The manufacturers are lying to us. It's something that's being done intentionally. The use of this data rate or physical rate as the advertised speed is something that goes back decades, from the days when everything was just wired and there was very little overhead, so there was very little difference between the two. And unfortunately, that's carried over to Wi-Fi, and it gets misunderstood a lot. And then on top of that, of course, oftentimes your RF environment or even your device you're using to do the measurement isn't even capable of hitting the maximum speed or maximum data rate because it doesn't support enough spatial streams or because it's too far from the access point or the signal-to-noise ratio isn't good enough. So that causes a lot of confusion and a lot of complaints from end users, whether it be on Amazon or whether it be to a Wi-Fi installer who's installed a new network. So it's something to try to understand what the differences are here and be able to explain that to your end user. So now I want to talk about how do we increase Wi-Fi speed. Now, I'm not coming at this from your perspective or an end user perspective, what you can do in the real world. I want to talk about it from a technology perspective. How do we go from 11 megabits per second in 11B up to 300 megabits per second in 11N versus, Wi-Fi 6, which theoretically can get up to almost 10 gigabits per second. So how do we increase the speed from a technology perspective? So one of the ways we do that is by increasing how much data is being encoded into a certain amount of bandwidth. So this is measured as QAM. So you've got 64-bit QAM, which is what was used in 11N. The move to 11AC opened up 256 QAM, and now with Wi-Fi 6, we've got 1024 QAM. So as that goes up, the more data you're cramming in there. The next thing we have here are called spatial streams. And spatial streams, I'll talk about here. We've got a slide that explains them a little bit better for you. And then the other way is increasing your bandwidth. So 11G had 20 megahertz channels. 11N gave you the option of using 40 megahertz channels. And then 11AC gave us 80 and 160 megahertz channels, depending on which generation it is. So let's go a little bit more in depth into this, and we'll start by talking about bandwidth. So most of your Wi-Fi devices are operating in 2.4 and 5 gigahertz. You've got two radios, one operating in each. A lot of legacy devices and a lot of your smart home devices are using 2.4 still to this day. So in America here, we have officially 11 channels that are available for us to use. So when you go into the GUI of most devices, you will see a channel listing of 1 to 11. The problem here is the overall available bandwidth is around 60 megahertz, and a Wi-Fi channel is using around 20. So what that means here is in the real world, channel 1 overlaps with channel 2, channel 3, channel 4, channel 5, etc. So you don't really have 11 non-overlapping channels. You really only have 3 channels that you can use in the environment before you start getting overlap and interference between different devices. So as I mentioned with 11N, we started being able to use 40 megahertz channels. But again, there's only 60 megahertz approximately available to be used. So that means as soon as you add a second device, you've got overlap in frequencies being used by those two devices, and you're going to have interference issues. That was why there was a big push towards the later days of 11N from single radio 2.4 devices to what is now super commonplace today, which is dual radio setups that support 2.4 and 5. And that was because 5 gigahertz opens up a lot of channels for us to use without having to worry about interference. But of course, not all of your devices are going to support 5, so you've got to still have that 2.4 radio, again, for legacy devices, for smart home devices, etc. So now you've got, I think it's 26 non-overlapping 20 megahertz channels that you can use. Right, so that's much better than 2.4. Obviously, the drawback is as frequency goes up, range goes down. So 5 gigahertz doesn't have the same amount of coverage area as 2.4. So for that reason, many devices, even if you have a 5 gigahertz capable device, you may end up using the 2.4 radio if you are out of range of the 5 gigahertz provides. But I want to draw your attention here to this section here that's highlighted in orange, which consumes most of these channels. And these are called Vfs channels. So what are these Vfs channels? So basically, this 5 gigahertz spectrum previously required a license to operate, and it was specifically chunked out to support radar activities. There's some other stuff too, but it's mostly being used for radar. So that could be military radar, can be your local airport radar, it can be your local TV stations, Doppler radar for weather. They were using these frequencies. So when the FCC decided to open them up, they got complaints from the people saying, hey, we are already using this frequency. It's going to cause problems. It's going to, hurt our performance. Our radar isn't going to work right. So what the FCC did is it came up with this spec for DFS. Was it dynamic frequency selection? I think could be wrong on the S. And basically creates these rules. So if you're going to use these DFS channels, you have to follow some different rules than you would with the other channels. So one of the things you have to do is you have to verify that no legacy users are currently using the channel you want to broadcast on. And you have to stop and listen to it. And I forget the amount of time, but it's not a short amount of time before you can start broadcasting on it. And then if your access point at any point thinks it hears a legacy device, it has to stop broadcasting. So when it does that, it has to switch to a different channel. So if it switches to another DFS channel, it has to stop and listen and verify that channel's not in use before it can happen. So because of that, when you use DFS channels, you run into situations where your users randomly lose their connection for 10, 30 seconds, something like that, depending on how you've got things configured. So that obviously can cause some complaints from your end users who don't understand why every now and then their 5 gigahertz connection goes down. Another problem you run into with this is it adds about 6 months to the FCC certification process. So because of that, a lot of consumer devices don't bother getting support for DFS. So what you run into out in the real world is if people are allowed to bring their own device into the office environment, is you run into situations where some of your users can't connect to the 5 gigahertz radio because their device doesn't support these DFS channels. And you usually are not going to see this on the data sheet or on the product listing. It's not going to be until you've ordered some and try to connect that you run into this issue. So for those two reasons, a lot of people choose not to use these DFS channels. They prefer just to stick with these non-DFS channels. So now you're dropping from, I think, 26 channels that don't overlap down to, what is it here, like 9? So it reduces, how many devices you can deploy before you start running into interference issues. So it's not necessarily as wide open as it looks. And then, of course, as we were talking about before, one of the ways you increase speed is you increase the amount of bandwidth you're using. So if you go up to 40 megahertz channels, again, this is very old. This is 11N technology. You've now got just 4 non-overlapping channels that you can use. As we make the jump up to 11AC and 80 megahertz channels, you've now got 2 non-overlapping channels to choose from. So as soon as you add a third device operating at 80 megahertz, you will have interference issues. And of course, there's now support with 11AC Wave 2 and Wi-Fi 6 of 160 megahertz channels, which have to operate in DFS. So that means if you're using 160 megahertz channels, you run the risk of your Wi-Fi going offline for short periods of time at random, or depending on how the AP is coded, being able to dynamically drop down to an 80 megahertz channel over here. So that's it for bandwidth. Now let's talk a little bit here about spatial streams, because this confuses a lot of people. So in the old days of 11B and 11G and 11A, we had this thing that we hated. It was called multipath. Now, if you remember what I talked about before, your radio waves sort of radiate out from the antenna, and they interact with the environment. So we'll say this is our access point, over here is our client device. And as you see, the RF signal can take multiple paths simultaneously. So some of the signal goes straight and goes right to the device it's trying to communicate to, but some of that signal also hits stuff in the RF environment, bounces off of it, and then gets to the receiver here. And because the distances are different, right? Because this, if you're going straight to it, you've got a nice short distance. But this other signal went out this way, bounced off of something, and then came back. It's a longer path that it's taking. So you've got multiple paths that the same signal is taking, and it effectively creates an echo effect. And I'm sure everyone here has been into a room that echoes a lot, and it's the exact same thing. You've got sound going out, hitting different surfaces at different distances, and then reflecting back. And it creates sort of an echoey thing. And that was a huge problem in the early days of Wi-Fi. And there was a lot of focus dealing with, well, how do we neutralize multipath? And eventually some people smarter than me came along and said, hey, you know what? Multipath isn't a problem. Multipath is actually a benefit that we can take advantage of. So basically, they figure that because we're taking these different routes, the signal's taking these different routes to get to the same place, what we can do is we can send different data on each antenna. They will take different paths, and then the device listening is able to take those different signals and combine them together into basically one faster stream. So these are your spatial streams. So the spatial stream is telling you how many different paths you can transmit and or listen to and combine together. So we saw this primarily with First started seeing this with 11N products. They were able to do 2 spatial streams. So a single spatial stream with 11N is 150 megabits, and then you could combine 2 together to get 300. In some cases, you could combine 3 streams together, where previously these antennas would all be transmitting the same thing, although sometimes you would only actually transmit on just one of them, but I guess I'm getting a little too complex there. But so those are what spatial streams are, being able to use the same frequency to send different data at the same exact time to get faster combined speed. And then with 11AC Wave 2, we introduced something called MU-MIMO, multi-user, multiple in, multiple out. So again, we're using the same idea of multipath, and we're sending different spatial or different data streams on different antennas, even though they're on the same frequency. And the client devices are able to differentiate those signals because of the difference in time it takes for the signal to get there. But with MU-MIMO, instead of combining those signals together, we send different data intended for different client devices. So this is what we would call downlink MU-MIMO. This is what all your 11AC Wave 2 devices can support. It's from the access point to the client device. So again, you're still transmitting the same amount of data, 300 megabits. It's just now it's split between those users. So when you're looking at business class product data sheets, you will usually see the Wi-Fi not quoted as a speed, where a consumer device will say AC 1750. Most business devices will say on the spec sheet 3x3, 3x3 11N, or whatever it happens to be, 3x3 11AC. And basically, they're just telling you, here's the number of spatial streams this device supports. So you will usually see a number like 2x2 or 3x3. So the first number, I believe, is how many of those are transmitting. Second number is how many spatial streams your device is capable of listening to. Most access points, it's going to be the same. You'll see 2x2, 3x3, 4x4. There is an exception. Sometimes you will see something like this down here where it says 4x4:3. Cisco is the one that mostly you see this with. So what does that mean? What that means is not that you've got 4 spatial streams. It's telling you you've got 4 antennas that can transmit, 4 antennas that can receive. The number after the colon, though, is how many of those can be used simultaneously. So basically, in those cases, you've only got 3 spatial streams. So it's something to keep in mind. The reason they do that is Cisco doesn't use smart antenna technology, so their kind of way around that is to say, well, we'll have 4 different antennas that can hear the signal, and we'll choose the 3 that are working best at that moment as a way to try to boost performance without boosting the spatial streams. When you're looking at client devices, though, it is really common for these 2 numbers not to match. Generally, the first number will be smaller than the second number. So why is that? And it's because on the mobile devices, you don't have a lot of separation between your internal antennas often, and you're also generally trying to keep the power utilization of your mobile chips as small as possible. So it's easier to listen and decode the data than it is to sort of transmit it out on different spatial streams. So you will often see like 1x2 or 2x3. So the device is capable of downloading data faster than it's capable of transmitting data back on. So here's a little, cross-reference sheet here showing you with the different levels of QAM, the maximum speeds that you are capable of achieving. So you can see there's a lot that's going to go into determining the maximum speed your client device can connect at. So one is going to be the spec. How many spatial streams can it listen to? Then you've got your modulation type, and this is primarily determined by the technology, whether it's 11N, 11AC, Wi-Fi 6, etc. The challenge is, and then the bandwidth here. So the challenge we run into here with modulation is in order to be able to achieve these faster QAM rates, the signal to noise ratio needs to be pretty good. If the signal quality isn't good enough, one of the ways your devices cope is by reducing the encoding rate. So that is one way where a poor signal will slow things down, is it may prevent you from hitting that modulation rate you need. And then the other thing is you'll often see some sort of dynamic utilization here where, you know, it may drop from 160 megahertz to 80 megahertz based on the RF environment. So you may see things like that. So it may not be possible for you to hit the maximum speed with your client device, just based on whether your client's device supports the right number of spatial streams and whether the RF environment supports the highest levels of encoding. But anytime you're looking at a data sheet or something, it's always based on the maximum combination of these three things. So another common question we run into is how many devices can I get on one access point? And the short version of this is it depends, but it doesn't usually depend on your access point. So there's usually, there are some exceptions obviously, but in general, your access point is not the limiting factor. And I'm talking about combining like with like. If you combine a $50, 11 AC access point with a similarly spec'd $500 access point, you're not going to run into a difference. Now, if you look at the data sheets, you will often see differences. You will see data sheets making ridiculous claims like 512 devices or 1,000 devices. You're never hitting that in the real world. In the real world, when it comes to things here, it's the RF environment and the RF technology being used that is the limiting factor, not the horsepower of your access point or what's being slapped on the data sheet. So when the data sheets claim those huge numbers, it's just based on memory allocation. How much memory have we decided to allocate to the association file, essentially? You're never going to get close to that with most devices. And we'll sort of go through why that is here. And basically it comes down to airtime utilization. Again, as we talked about before, only one device gets to transmit at a time, and it is not the most efficient way of determining who gets to transmit. So as you add more and more devices, you are going to run into more and more conflicts. And like I said, in general, you're going to run into those conflicts long before you get anywhere close to the maximum users listed on the data sheet. So here's an example. We're taking the same situation here. We've got users watching a 3 megabit per second Netflix stream. So how many users can watch a stream at the same time? And the only thing we've changed in each of these scenarios is just the spatial stream. So all the devices in this theoretical scenario have the same signal strength, have the same technology, except for the spatial stream supported. So what you see here is if you have a client device that also supports 3 spatial streams, you're able to have 34 laptops on this access point and be able to maintain this 3 megabit per second stream. It works good. You get an aggregated throughput of 100 megabits per second. Take away one of those spatial streams, and now only 21 devices are capable of maintaining that 3 megabit stream. You are ending up getting only 65 megabit per second aggregated throughput. Reduce it down to just a single spatial stream device, and now you're down to just 10 devices on that access point and 30 megabits aggregated throughput. And in the real world, it's much more complex than just the spatial streams. You're going to have a mismatch. Some devices that support 3, some with 2, some with 1. You're going to have other things factoring in here. If you're getting a lot of users communicating at the same time, you may be running into airtime utilization issues. You may be running into those hidden node problems we talked about before, all of which are going to degrade performance even more. So it's really hard in the real world to tell you how many the users are going to get there. It's going to depend a lot on what are the client devices capable of, what are those users trying to do. So obviously, if you've got a bunch of like smart home devices that only transmit tiny amounts of data sporadically, you're going to be able to fit a lot of them on there and not notice any performance issues. Contrast that to if you're trying to do voice over Wi-Fi, you may run into a lot of issues. Even though voice over Wi-Fi doesn't use a lot of bandwidth, Most voice over Wi-Fi streams are less than 100 kilobits per second. So why is it you can't get a lot of them on there talking? And it comes back down to what we were talking about before. Only one device can transmit at a time. And voice, unlike watching a stream, you aren't able to buffer a voice conversation. That adds latency, and it's hard to have a conversation with somebody when they're hearing what you're saying a second or two delayed. It's also very important with voice that the packets being sent all come through in order. So if you run into a situation where there's interference and you drop some packets and then you send them again, you can't really do that with voice, where with streaming, you buffer that, and you can recombine things before your device gets around to playing them back. So voice over Wi-Fi is one of the toughest things to deploy out in the real world, even though the bandwidth utilization isn't much, because you're running into issues with drop packets and just poor airtime utilization. So now I want to talk a little bit more about co-channel interference and one of the technologies Zyxel offers to solve those issues. So I've already kind of explained this before. When it comes to Wi-Fi, when it comes to any sort of radio things, if you have only one device gets to transmit at the same time on the same frequency. Another way of visualizing this that many of you may have encountered is if you've ever gone on a road trip and you listen to AM radio at night, you run into situations where you've got two radio stations using the same channel or using neighboring channels, and it becomes unlistenable because they keep fading in and out to each other, the volume goes up and down. That's the same thing again with Wi-Fi here, with these radio waves that Wi-Fi is using. And as we've talked about before, especially on the 2.4 radio, there's a very limited amount of channels you can use before you start overlapping with nearby devices. So one of the ways you dealt with this historically is you drop the power. So you've got two APs here. You can see the signal coverage area here. You drop the power, so now they are not interfering with each other. So this is one of the main ways we've traditionally tried to deal with this. And it does reduce interference, but it also lowers your signal-to-noise ratio. So you may end up trading one problem for a slightly different problem, which also harms your performance. So your traditional access point has what we call a fixed antenna, and usually it is a omnidirectional antenna coverage of some pattern. You'll often see this being referred to as umbrella coverage. Basically, you've got this nice round coverage area emanating out from wherever your access point is. So with smart antenna, we do something a little bit different. And with smart antenna, you've got this intelligent antenna system that has the ability to use hundreds of different antenna combinations. So with our smart antenna combination, we're able to determine which antenna pattern is best for the client. And our algorithm that we use is heavily optimized towards co-channel interference issues. So not only is it trying to focus the antenna or the signal towards where the client device is, it also is keeping track of sources of interference, whether they be other APs or whether they be industrial devices that put off RF like microwaves. So it is not listening in the direction that that noise is coming from. And the cool thing about smart antenna technology versus something like, say, beamforming is it doesn't require anything special on the client. Any client device can take advantage of it. It is entirely an AP technology, and it also works with moving devices. So even if the user is mobile, smart antenna is able to constantly change the pattern being used to the best one based on that current environment. So we've got some testing here that we've done. So this is sort of your typical modern day hotel scenario. Historically, the way hotels had worked is you would put an AP in the hallway, and it would cover anywhere from 4 to 8 rooms, depending on building material. In some cases, if the floor allowed RF to transmit through it or the ceiling did, you may even get up to as many as 16 devices. So that was your typical umbrella coverage pattern back in the 90s, early 2000s, when there weren't a lot of mobile devices being used, and they were primarily being used to download emails and browse the internet. But now, as more and more users are bringing more devices into the room, they're trying to stream Netflix, they've got video ads loading in the background, whether they want them or not, etc. that methodology doesn't work. So what we're seeing here is most mid-tier and higher hotels are going to a situation where they're putting one low-powered AP per room, or one per every other room. So in this scenario, we've recreated your typical hotel environment where you've got one low-powered AP per room. We are using the 5 gigahertz radio frequency non-DFS channels to minimize overlap of nearby access points. And we're testing this out. So the devices we're using to test this was our, I believe it was our NWA 1302, which has now been, and a Ubiquiti, I forget the model. I think maybe we tell you on the next slide here. But there's similar models, the UAP ACIW. They've both got essentially the same form factor. They've both got essentially the same RF performance on spec, right? The same output power, or similar output power, similar RF sensitivity, and so we started testing them in this environment. So first off, we start with one AP, and you'll see here Ubiquiti slightly outperform us. They beat us by 2 megabits per second in aggregated throughput of users on these APs. Both were roughly around the same at 67% airtime utilization. So what happens now when we add a second AP a couple rooms down on that same channel? And you'll see here the aggregated throughput of the two devices. And you'll see now the aggregated throughput between our device and the Ubiquiti device significantly different. 785 megabits per second aggregated throughput on Zyxel versus 555 megabits per second, or megabits aggregated throughput on the Ubiquiti. Now, the only real difference between these two devices is that we're using a smart antenna and Ubiquiti is using a traditional antenna. And I'm not picking on Ubiquiti. You will run into the same problem with, say, our WAC 500H, which is a similar form factor and also does not have a smart antenna. And you see here when we look at the airtime utilization, Ubiquiti is at 95%, which is really good, right? But we've been able to go above the theoretical maximum and get up to 131% aggregated throughput. And that's because the smart antennas are behaving in such a way that you can have multiple devices transmitting at the same time, nearby each other on the same channel, and we're able to ignore that interference, essentially. Now we go and add a third AP. This one's actually on a different floor, but it still provides some level of interference. And again, you'll see here our aggregated throughput has gone up now to over 900 megabits, where the Ubiquiti is basically capped out and similar to what it had before at 544 aggregated throughput. Another thing to draw your attention to is look at the aggregated throughput per AP. You will notice with smart antenna, very similar performance between each one of these APs, whereas when you're looking here at the non-smart antenna access point, it is really not evenly distributed what's being used there. And again, our airtime utilization has gone up even more now, up to 155% of the theoretical 100% maximum airtime utilization. So these are the benefits of smart antenna. So this is really good for environments where you've got lots of interference issues, whether it's other APs in the nearby area. It's really good for things like conference centers, expo areas, anywhere you've got a lot of access points in the same area, anywhere you've got a lot of users in the same area, it makes a huge difference. So Paul Cook had a question here. I'll go ahead and answer Paul's question. If it makes sense for a hotel to have an AP per room, why not offices and businesses? And it very well may make some sense for you. It is not a trend I have seen. I think the primary difference you run into here is going to be in a hotel environment. The signal is often having to go through multiple, let's go back a couple slides. You know, your user is over here, and if you do it the traditional way with an access point over here, the signal's got to go through this wall and out to the AP. And a lot of hotels, this wall over here is where your bathroom is, so you've got pipes, you've got ceramic tiles, you've got all sorts of stuff. So the signal isn't able to get back out to them too far. Whereas in an office scenario, you are generally looking at sort of a cubicle type environment where you've got, which doesn't cause that much loss compared to pipes and ceramic walls. Also, the walls inside of an office generally tend to be hollow, where again, these outer walls in a lot of your hotel environments are filled with conduit and pipes and things like that, which again are going to cause more of a sort of interference issue. So I think those are probably the two big reasons why you don't see this sort of move in an office environment, just because the signal is capable of going much further. Also in an office environment, I think there's a lot less variability on the client devices, and the IT staff generally has a little bit more control. So, you know, most businesses standardize on certain models of laptops, certain models of tablets, whereas in a hotel environment, you've got, you know, just a huge mishmash of devices that can be in there. But there may be situations where multiple low-powered access points do make sense in certain type of office environments, especially like older buildings where they've got the internal walls are solid construction using brick or using really thick plaster, things like that. It may make a lot of sense to do it, or where instead of cubicles in a big open area, you've got, you know, multiple small walled-in offices. So there absolutely are, I think, situations where it may make sense, but I certainly have not seen a trend towards that in office-type environments. Another technology to talk about here that we offer is something called dual optimized antennas. As far as I'm aware, we're the only guys who offer this. So again, as I talked about before, you know, most APs have a single antenna pattern that's designed for mounting the access point on a ceiling directly above the, or directly centered in the area it's trying to cover. However, as we all know out in the real world, you can't always mount your access point on the ceiling. Sometimes you've got to mount it on the wall. So when you do that, you tend to get less than optimal coverage patterns. You end up sending a lot of signal up into the floor and into the ceiling, and either losing it or causing interference to your neighbors upstairs or downstairs. So one of the things we have here is something called dual optimized antennas. We have built an antenna into the device designed for ceiling mount, and we've built an antenna into the device for wall mount, and we let you switch between which antenna you want to use. So that way, you know, those you can standardize on one device, and you can simply switch the antenna pattern based on where you've installed that particular access point at. And again, I think we're the only ones that have that. I know on smart antenna, Ruckus also offers smart antenna, but I don't know of anyone doing the dual optimized except for us. If you know of someone that is, let me know. But yeah, so then just in general, when it comes to mounting, you know, access points, ideally you're going to mount them on the ceiling, and you usually are going to try to mount them within reason as high as you possibly can. And the reason you are doing that is you're trying to avoid the signal having to pass through obstructions. So generally, the higher you mount it up, the less obstructions you're going to hit, the less cubicle walls it has to go through, the less people walking around it has to go through. So generally, that helps your signal to noise ratio. And again, you try to want to make it centered because most access points are going to be providing 360-degree coverage emanating out from them. Now, one thing we run into, and this is going to depend on your local building codes, is we often hear the complaint, you know, my customer doesn't want me drilling holes in the drop ceiling to mount the antenna onto the drop ceiling. Right, most of your offices have a drop ceiling where you've got T-bar up there, and then you've got these acoustic tiles. Now, if your local building code allows it, you can mount the access point above that drop ceiling. And we have had good luck with people simply laying the access point on top of the drop ceiling. So that way, people in the room don't see the access point. You're not drilling holes to run cable through. It is something you can do. Most of your typical standard acoustic tile up there is essentially mashed up cardboard or fibers, and it doesn't provide much degradation to the signal. So you can put it up there and it works. Obviously, you need to take into account what else is up there. Ductwork, metal ductwork is horrible when it comes to, blocking RF signal, your light fixtures, things like that. And then also, if you are mounting on a real ceiling up above the drop ceiling, or maybe there is no drop ceiling, same thing. You may actually want to not actually mount the AP onto the ceiling. You may want to get a pole and mount the AP on the end of the pole, because oftentimes those ceilings have a lot of conduit and ductwork up there which can block the signal. And there are third parties out there that provide various types of drop-down masts. So you put this mast essentially on the ceiling, it drops it down 3 feet or 6 feet to get beyond all the stuff up there on the ceiling. So you've got a nice clean RF environment for your AP. So again, as we talked about before, the traditional way of doing hotels, and we still see this being done particularly at sort of your lower tier hotels, your Best Westerns, things like that, is umbrella coverage, where you mount the AP in the hallway and hope it covers a bunch of rooms. Now, as we talked about, one of the challenges with that is those outer walls tend to have a lot of stuff in them, and oftentimes the guest experience has the signal going through multiple walls. We just helped troubleshoot one of our partners where I want to say it was something like up to 8 walls the signal was having to get through to get to the access point, just based on the configuration of the rooms for those edge cases out here. So generally, most of your higher end hotels are getting away from that and moving to 1 per room or 1 per every other room. And there are a number of different access points out there from us and other vendors that are specifically designed for this in-room deployment. Another nice thing about doing this in-room deployment is the access points that are designed for this tend to have pass-through ports and pass-through PoE. So you can run one Cat5 or Cat6 cable to the room. It goes into the AP through a junction box on the wall. The AP covers up the junction box, and then you've got Ethernet ports out. One can go to your IPTV in the room. Another with PoE can go to your in-room IP phone. So you're just running one Cat5 cable per room, and then being able to provide both guest access and hardwired access for phones and TVs in the room. So that's something else as another driver for going to this one AP per room scenario. In general, when you're mounting stuff where people can get to it, you want some sort of locking mounting option, something where it's not obvious how to remove the access point from wherever it's mounted. Guests will steal anything that they can get their hands on. The other thing to run into is you want to also look, if you can, if you're mounting on ceilings in particular, that the AP allows you to turn off the LEDs. People don't like seeing flashing lights when they're trying to sleep. So something else to keep in mind. In public areas in a hotel, lobbies, restaurants, pools, things like that, generally the main thing to keep in mind is going to be user density. The more users you have, the more APs you're going to need, so you can distribute those users across the APs. And the more users you have, the more you might think about moving to a smart antenna-based solution. When you're setting up things like load balancing and client steering, you want to do them based on the physical area. You don't want everything set up as one node in the hotel, so you end up with your APs trying to load balance between the lobby and guest access up on the 9th floor. You generally are going to want to segment those out into groups within the hotel for your load balancing and client steering. And also, in general, each area should be planned out by itself. Even though the lobby and the hotel restaurant might be right next to each other, treat them as separate areas and customize based on the individual demand in those areas. And again, anywhere where you've got a lot of APs or you've got a lot of users, really consider using smart antenna. It makes a huge difference. When it comes to schools, one of the first questions you want to ask is, how many students are in each room? You do want to have the APs installed in the room itself. And then the other question is, is it a smart classroom? And it varies a lot, maybe from school to school. It may also vary depending on what room they're in. So certain types of classes may be taught in smart rooms where other classes are not taught in smart rooms. And what are they doing with them? So does each student have a laptop? Does each student have a tablet that they're using in class? And then how much is it actually being used in class? We've seen situations where rather than broadcast or project a movie onto a big screen in front of the room, teachers are streaming to each individual device's or student's own screen, or where the teacher is taking over each student's screen simultaneously and remote controlling things. So, in those situations, you're going to need a lot more bandwidth. You're going to have a lot more devices online than in a classroom where students are really only getting on their mobile device to take a test, or at the end of class where they're browsing the internet and doing research on Wikipedia type stuff. So, find out on a per room basis, how are things being used? And, take into mind the same considerations you would for any other Wi-Fi deployment. Basically, the more bandwidth that's being used, the more users that are simultaneously trying to use the internet, the more APs you need. Generally, if a classroom gets to 20 students or more, you need to use 2 APs per room. And if you've got 30 or more students in a room, you generally want to use a smart antenna solution. Our products do have a special load balancing mode specifically designed for use in smart classrooms. It's basically optimized for the idea that, every 45 minutes to an hour, you're going to have 30 or 35 kids come into the same space and all connect to the network at the same time. So I want to talk a little bit about 11AX. I know it's been around for a few years now, but we still do get a lot of questions on it. When it was first making the rounds back in the day, it was being promoted as high-efficiency Wi-Fi. These days, it's being called Wi-Fi 6, and of course, you'll see it referred to as 802.11ax. Now, the reason they called it high-efficiency Wi-Fi is it was designed to solve a lot of the issues that Wi-Fi has been plagued with since the late 90s when the first 802.11 spec came out. It's been designed to solve these issues of a lot of APs in the same area or a lot of users on the same AP. So many of the same issues that smart antenna is also designed to solve. Now the nice thing here is you can combine smart antenna and Wi-Fi 6. They have the same goal, but they're going about it in different ways, and they are complementary ways. So it's something to keep in mind when it comes to Wi-Fi 6. Also, all of these advantages that you get with Wi-Fi 6 require your clients be Wi-Fi 6 as well. So most of us have a mixed environment where you've still got 11N and AC devices, so you will not see all the benefits of Wi-Fi 6, particularly when it comes to being high efficiency in a mixed network environment. Some of the cool things here with Wi-Fi 6 is it works on all of your frequencies. It works on 2.4, it works on 5. Whereas before, 11AC is only a 5 gigahertz technology. Your 11AC access points and routers are still 11N on the 2.4 radio. So Wi-Fi 6 has the potential to make a huge upgrade on that 2.4 radio. And there's a bunch of cool things that are giving us these benefits. As we talked about before, there's higher levels of encoding. We've added what's called Ofdma. It allows us to more flexibility in being able to chop up the available spectrum. So you're only using the spectrum that you need, and you're assigning that spectrum based on the needs of the user. And it finally gives us the ability to do uplink MU-MIMO. So with 11AC Wave 2, you can have your AP send data to multiple clients at the same time, but then the clients each have to take turns. So with Wi-Fi 6, now clients can transmit data simultaneously to the same AP by using different spatial streams. We have the ability to tag and reuse spectrum. There's a lot of cool stuff that's in the Wi-Fi 6 spec, and it is probably easily the single largest single generation improvement when it comes to Wi-Fi going forward. So when it comes to Wi-Fi 6, the initial working group approved it all the way back in Q4 2020, and that's when you started seeing Wi-Fi 6 devices hitting the market, although they are missing a lot of features. The actual Wi-Fi 6 spec was not finally approved until Q1 of 2021, right, about a year ago. So there's been products calling themselves Wi-Fi 6 for years before there's actually a finalized spec. And a lot of those early generations of products are missing some of the key features that became part of the final version of the spec. Some of that was just because the spec wasn't finalized close enough, and a lot of it's just it takes time to engineer the chips and manufacture the chips to be energy efficient and offer all of these sorts of features. For instance, that's uplink MIMO functionality. That was only actually added to the Wi-Fi 6 certification this month, just now. It's just been added last week. So before, Wi-Fi 6 certified products may also be missing some of these important Wi-Fi 6 features, even if they were certified. Which leads us to, when is Wi-Fi 6 not Wi-Fi 6? So some of the challenges we've run into here is there is no body policing what people are calling Wi-Fi 6. Some of you who follow cellular technology know there's always been problems with people calling stuff, 4G that wasn't true 4G, 5G that isn't true 5G, and we run into the same thing now with Wi-Fi. There is Wi-Fi 6 that really isn't true Wi-Fi 6 product. Well, we've run into this in the past with other technologies, right? When 11N came out, we ran into the same scenario, but we were lucky enough that most vendors were nice enough to call these early 11N sort of products pre-N, right? You would see that on the box, pre-N. And with 11AC, we had Wave 1 and Wave 2 to denote different sets of features. So for when it comes to Wi-Fi 6, those first guys that were launching the early Wi-Fi 6 product didn't call it pre-6 or pre-Wi-Fi 6 like we did back in the 11N days. They simply called it Wi-Fi 6. So it causes confusion because when you're looking at a product, it's hard sometimes to tell which Wi-Fi 6 features are actually supported and which ones aren't. Now, one of the ways to do that is just, to look at the chip and how old is this chip. If it's an older chip, if the chip's more than, a year, 18 months old, when it hit the market, it's probably missing some key features. But even some of the new products are missing some of these key features. So I'm just showing you here Qualcomm, their Gen 1 versus Gen 2. Very similar to Qualcomm, you'll see you're missing these uplink MIMO, you're missing uplink OFDMA, you're missing BSS coloring. So these are some really important features that you are missing out on some of these devices that are using the older chips. Another thing you're running into is, as I mentioned before, Wi-Fi 6 is the first technology since 11N that improves 2.4 performance. Some vendors out there are only putting the Wi-Fi 6 features on the 5 gigahertz radio, and they're still shipping old 11N on the 2.4 radio. So that is something to keep in mind. Ubiquiti is one of the vendors doing that. And you are still seeing, for instance, Ingenious. Most of the Ingenious Wi-Fi 6 products on the market are using the older chips. And some of the brand new Netgear business APs are using those same older generation chips. So why are people doing that? And the main answer here is cost, right? The ability for vendors to come out with a sub-$100 AX1800 class product is by using these older, cheaper chips. So when it comes to Zyxel, all of our NWA 110, 210, 510, 610, 650, all of those products support the full Wi-Fi 6 feature set. They are all using the latest generation chips that support all of these features. We do have two products that do not support all of these features, and again, the reason for this is these products are aimed at this sub-$100 Wi-Fi 6 market, where we're competing with inexpensive Netgear and Ubiquiti products that also don't support the full feature set. So those products are the NWA50AX and the NWA55AXE, which are currently Amazon exclusives, and our new NWA90AX, which will be coming out in a month or two, that will be available through all of our channels. So again, with the exception of those three models, everything we've got is using the full Wi-Fi 6 feature set. And Michael Prince here is asking about 6 gigahertz. So let's talk about 6 gigahertz. Wi-Fi 6 6E. So this is something that the Wi-Fi Alliance has come out with here. They've opened up this 6 gigahertz spectrum for unlicensed use. So that is being, and as we mentioned before, Wi-Fi 6 11AX can work on 2.4 and 5, and it is also future-proof. So it can be used in theory in just about any frequency range. So Wi-Fi 6 technology can be used in the 6 gigahertz spectrum that has been opened up. So the benefits of this spectrum here are it is huge, right? 1,200 megahertz of spectrum. That gives us 7 non-overlapping 160 megahertz channels versus 5 gigahertz where we've got 2. So it's going to be a huge benefit in these high density deployments. So you can have each AP, you can have up to 7 different APs in an area, all using non-interfering channels. It's going to be a boon there. Of course, the frequency has gone up, so the range and the ability for the signal to penetrate through physical objects is going to be reduced from 5 gigahertz and 2.4. So that's one of the challenges we're going to run into. And much like 5 gigahertz already had legacy users, particularly radar, 6 gigahertz has been being used by licensed use, in particular utility companies with smart utility, smart meters, and being used by mobile news reporters. So when you see those mobile, a reporter out on location someplace, they are using and have been using for a long time this 6 gigahertz spectrum. So rather than DFS, which, like I said, has some significant performance issues and risks of users being turned off, 6 gigahertz has their own thing called automated frequency control, which kind of does the same thing. It tries to reduce the chance of your network causing interference to these legacy users of the spectrum, but it does so in a much less intrusive way than DFS did on 5 gigahertz. So you shouldn't have as many sort of disconnection issues. It shouldn't be a problem now with 6 gigahertz. Now, the challenge we run into with 6 gigahertz is it's not a firmware update. You need to have a dedicated 6 gigahertz chip that can produce 6 gigahertz frequencies, and you need to have dedicated antennas that are optimized for 6 gigahertz use. So now you're going to run into situations where with 6E, some devices may only have 2 radios, some devices may have 3. So if you've got a 3 radio device, you're going to be able to have 2.4, 5 gigahertz, and 6 gigahertz all operating at the same time. So the cost is going to go up, right, because you've now got 3 different Wi-Fi chips operating at the same time, but you've also got to make a significant boost to your main CPU because of just the aggregated throughput that can be going through all 3 of those radios at a time. So it's going to also become much more important for you to have a multi-gig network that you are using. Realistically, you're going to want to have at least a 5 gigabit per second physical wired network so that your wired network doesn't become the bottleneck to your wireless network going forward. There are Wi-Fi 6E devices out there today. They are primarily aimed at the consumer market at this point. We had hoped that we would have Wi-Fi 6E devices for business use by now. Unfortunately, we are not happy with the chipset solutions that are currently out there and the state of the SDKs from the chipset vendors. So we are keeping an eye on this space. We need a chip that is stable enough for business class use and has all of the features that our other Wi-Fi devices have, particularly those of you using Nebula. We don't want certain features to not be supported, certain business type features to not be supported on the chip. So once the chips and the software is ready for, we deem ready for this market, we will have those Wi-Fi 6E products from Zyxel. It's really hard to say. Like I said, we had originally thought, based on the roadmaps we were given, that we would have those products by now, but it's not there. Hopefully by later this year, By the end of the year, we'll have something. In particular, we're looking at using them for outdoor usage. And then the other thing, again, is going to come up is some Wi-Fi 6E devices will only have 2 radios. So you'll probably have one 2.4 radio, and then one radio you need to select 5 or 6 gigahertz. It will be one or the other based on software selection. And then, of course, the client devices have to support 6 gigahertz. You have to have the client device that's designed for 6 gigahertz utilization. So at the moment, Wi-Fi 6E's got a lot of promise. It's not quite there yet, I think, for the most part, on the business side of things. It may be there on the consumer side, but again, how many of your client devices support Wi-Fi 6E? And I think the answer at this point still is there's very little out there. We're still seeing huge lag for upgrades to Wi-Fi 6 in general out in the real world, and on lower end devices are still not providing Wi-Fi 6, or if they are, it's only one spatial stream. So it's going to be a while before you have a significant number of users that can take advantage of Wi-Fi 6E. But it is coming, and it's got potential to be a huge game changer, especially in things like stadiums and big conference centers and things like that, expo centers, where you've got a lot of wide open space and a lot of users. You run into a lot of interference issues. Yeah, Michael here made a comment here where, consumers don't design their networks around 5 gigahertz properly, and 6 gigahertz won't correct that. I use what I call my one wall rule, meaning 5 gigahertz can penetrate one wall and only one wall, assuming sheetrock construction. And yeah, that's absolutely true. I mean, let's be honest. Your typical home user probably has a gateway, a Wi-Fi router that was provided to them by their ISP. It probably comes in and is connected to an exterior wall on one corner of their house. Consumers always just have it so rough, because nobody wants to spend the money to run Cat 5 to be able to more centrally position their access points. The mesh products try to solve that, but then you run into issues with, data having to be sent over multiple hops, which reduces your overall aggregated bandwidth. It's not a huge thing, but you are seeing this technology first on the consumer side, and that's always been what we've seen when it comes to Wi-Fi technology. Consumer vendors are always going to be the first to adopt any new technology, because there is a huge race to be the first one to market and to get that early market share. So 3 or 4 years down the road, when it becomes more widespread on the client side of things, that users have already associated your name with that technology, and you're the go-to for it. And it's something that's, honestly, is a story as old as time, or at least as old as Wi-Fi. One more question here. We're not quite on the question slide, but I'll go ahead and take it. Do we ever recommend using mesh instead of hardwiring each AP? Do we ever recommend it? No. Hardwired is always the best way to go. Having said that, that's not always an option. All of our APs do support mesh. Nebula provides mesh for free. If you're using our managed wireless LAN solution, I think it's included in the Wi-Fi license these days. It used to be a separate license with our NXC controllers. I think it's standard now if you're using a USG device for the controller. So it's there if you want it. And, we've got kind of a smart mesh feature, which is kind of cool with Nebula, where, you can have a hardwired device, and if for some reason it gets disconnected, it'll automatically switch to mesh mode and connect to another nearby AP that does have a working wired connection. So, there's benefits there for redundancy to make sure areas don't go offline. And there are just situations where you need to provide coverage in an area and extend a network, and the customer doesn't want to pay for a drop, or the materials don't allow you to run a new cable drop. It is an option for you. I don't recommend it if you can avoid it, but you can't always recommend it. The challenge you run into is just, you end up reutilizing spectrum, so you introduce some latency and you hurt your bandwidth available. One ways around that is to have a third dedicated radio just for mesh, but there's so few people using, in business side of things, using dedicated mesh links that we ourselves don't offer it, other vendors do. For homes, though, it makes a lot of sense, and for big homes particularly, If you're going to go mesh, I highly recommend you go with a true tri-band solution. It's going to cost you more money, but it makes a huge difference in performance, both overall bandwidth, but also if you have kids in the house doing gaming, it makes a big difference when it comes to latency. Compared to that, we just swapped out somebody's they have a 5,000 square foot house. We swapped out their Google Wi-Fi system, which is just dual radio, to a tri-radio solution, and it made a significant difference for them. They were trying to do work from home and were having all sorts of audio issues because they're trying to do voice over Wi-Fi, and it's the most finicky of solutions out there. Hope that answered that question. Onto the slide. That's the end of the presentation. Most of our webinars are recorded and automatically posted to our YouTube channel. There are multiple Zyxel YouTube channels from different regions, different countries. In the US, we're split between a service provider and a channel. This is the channel side of things, so we are a Zyxel America channel on YouTube, and then we're also on LinkedIn, so feel free to connect to us on LinkedIn. Otherwise, this is open for questions. And while waiting to see if there are any more questions coming through, I'll just go ahead and highlight something here. We do have user forums. You may not be aware of them. They're only within the last couple of years that we've had proper user forums. Forum.zyxel.com. You can go there, talk to other Zyxel users, resellers, installers. The nice things about the forum is that's where release notes get posted first. That's where security advisories usually get posted first. The forums are also monitored by our R&D, our tech support, and our PM teams. So when you post questions there or you post feedback or ideas, it is being seen not only by your fellow installers and users, it is being seen by people at our headquarters back in Taiwan. And we will occasionally answer questions or provide feedback. So it is something that you should probably check out if you haven't already. If staying up to date on firmware releases and release notes and security advisories, it is a great place to do that at. So keep an eye on that. And my email is Sean R, SHAWNR, @Zyxel.com. Feel free to reach out to me offline. We are always desperately looking for your suggestions as to what sort of webinars we can put together for you that you would find beneficial for yourself or for your team members. We really need your help, telling us what sort of additional information you'd like us to provide to you guys, so we can do that. So feel free to email me with that information. I don't have any other questions, so I'm going to go ahead and end today's webinar. Thank you for joining us. We just recently rolled out a new update to Nebula with some new features. I will have a webinar coming up, I think next week or the week after, where I'll go sort of in depth onto what those changes are. Please join that. And thank you again.